Hello and a very warm welcome from Physics for Students. I hope you're keeping well and safe. Welcome to another video on how to solve partial differential equations. This particular video we will be concentrating on solving problems which are related to partial differential equations. I think the viewers who are watching this video has already seen my previous video and have got some idea on the basic concept of what is a partial differential equation. In this particular video we would be speaking mostly about the definition, about the concept, about solving problems and seeing some geometrical representation so that we can understand what do we mean when we speak about partial differential equation. So first what we would do is that we would go forward with the basic definition of partial differential equation. Now as you understand, calculus is all about studying about the changes, the law of changes, and as I always tell, that change is perhaps the only important thing and the only permanent thing in this world, and all we human beings want to do is that get adapted to this change. So while studying calculus, because it is a study about changes, derivatives of functions of one variable, we find that one interpretation of derivative comes in which is most important, is called instantaneous rate of change. If you have seen my earlier video where I talked about the inception of the concept of derivative, it was basically how to calculate the instantaneous rate of change, not from one point to another but just taking one point and calculating that point's instantaneous rate of change, and that is how the concept of derivative evolved. So one part we are clear is that one is the instantaneous rate of change of y as a function of x. So we are using the Leibniz notation, in that case using dy by dx, which implies y as the dependent variable and x as the independent variable. Now suppose we have got a function something like this: z equals to function of x comma y. So how do we do with the Leibniz notation of dy by dx with two variables x and y? In this, that is why I have put a question mark. X and y are the independent variables and z is the dependent variable. So how do we use Leibniz notation of two variables? Now that is actually comes the problem, as we call that necessity is the mother of invention. So the necessity is basically to solve problems with two variables. However, Leibniz earlier notation and the maths that was already in place was only to solve problems with one variable. Right. So if we take a function x comma y with two variables, what we can do is that then the partial derivative, which is written in curly d at right hand side of your screen, of f with respect to x is written as del f by del x, or we can use this one, fx can be written as del f by del x, limit of h tending towards 0, function of x plus h comma y whole divided by h minus subtracted by fx comma y. So this is the entire idea which we have to keep it in mind when we are dealing with partial differential equation. We are dealing with one variable, we are keeping that variable constant, and then we are differentiating keeping the other variable constant. So as we have seen, z equals to fx comma y, there are two variables involved. So del f by del x actually tells the partial differentiation of f with respect to x. Now let us see what we do when we write f with respect to y. So here I have shown in this part in red, which actually shows that the denominator when we write as del x, that means the right hand side with respect to what x would be in the denominator and the previous would be on the numerator. Now we continue with this and we write f with respect to y. Simple, we write del f by del y. Function f sub y can be written as del f by del y instead of del x. We are differentiating with respect to y, and it follows limit of k tending towards 0, f of x comma y plus k minus f x comma y whole divided by k. So this actually gives you this idea. The first one was done partial differentiation with respect to x keeping y constant. Here we have done y keeping x constant. This is the basic idea, and all of the problems that we will see in the video will be doing keeping this particular concept in mind. As you have seen that I have given this picture of Leibniz because there was always, I won't say a tussle, but there's always a difference of opinion, a race between two great people, Newton and Leibniz, who actually discovered calculus. But if you take my opinion, it was Leibniz, not Newton. So the difference shows in this definition, there are two differences. First is this: d gets replaced with a curly d, which is the partial part. So the notation changes, although we are still within the realm of using Leibniz version of notation. The d is getting replaced by del, and del f by del x actually shows partial of f with respect to x. And we can always use this, that depending on the variable we choose, we can come up with different partial derivatives altogether. As we have got two different derivatives, we can take, since these are two different independent variables. So this is actually, now we are in the realm of partial differential equation, del being replaced by d being replaced by a curly del, and df by dx means partial of f with respect to x, and so on. So what we will do now is that we will look forward for a very general definition of partial differential equation. If we take a kind of a function which goes from x1 and goes up to xn, and this particular function happens in the direction of a1 up to an, then we can use this definition, del f by del ith element of x, limit of h tending towards 0, and it goes up to this whole divided by h. So this is a kind of a generic definition where we are considering n numbers of n number of variables in n directions, n dimensional directions. This particular definition comes useful. So if you look forward for the notations of partial differential equation, it is quite common that we are using subscript. So u sub xx can be written by del squared y by del x squared u sub xy, and in this way. So don't get confused if this type of notations are cropping up in your examination or your class notes or your study notes. These are all basically different notations of partial differential equation. However, this one on the left hand side I have written by mistake. It is not this u, it will be del u. So that is how it happens. Further, if I take another notation, function of x comma y, and it goes up to z, st, up to any number of variable, then these are also called notations of partial differential equation. So anything like del f by del x, or capital D sub x or f, or capital D1f, these are used, as you understand, in different cases depending upon the equation, complexities, dimensions, etc. So just to give you an idea that what could be the other notations of partial differential equation also. So this is the first problem which we will deal with. If we get a function x comma y, and it goes up to x squared minus 3xy plus 2y squared minus 4x plus 5y minus 12, then how do we calculate the partial derivatives from the definition? So from the definition means that we will be using what I showed you right at the beginning, the long one, the limit definition. And first we will calculate function of x comma y plus h. So we use this expanded x squared minus 3x y plus h, then plus 2y squared is y plus h whole squared, then minus 4x plus 5y plus h minus 12, which leads to this. So we have opened up, and I have used a plus b simple algebra formula, x squared minus 3xy minus 3xh plus 2y squared plus 4yh plus 2h squared minus 4x plus 5y plus 5h minus 12. So what I'm going to do is that, yes, this red arrow shows that I'm first going to differentiate in terms of y. So I'm going to substitute this entire long value on this limit on this formula. So what it would lead to is this. Yeah, it is a quite long one, so you can understand. Then I write this one. If you want to take a pause on this video, you can do and take a note, and you do it on yourself so that things become clear. Now I am eliminating the negative signs, plus and minus, so the negative and the positive gets cancelled off, and we are left with this. Okay, then we go further, and I show it in blue arrow that whatever is in the numerator is being replaced, and then del f by del y equals to this, and then this is the final result. So it is minus 3x plus 4y plus 5, and as k of limit of k tending towards 0, I have replaced this k with this value. What we'll do next is that we are going to differentiate in terms of x. It was previously y. So you see with x all this gets cancelled out, this gets cancelled out, it shows this and this and this and this. So again I would say if the viewers wants to take a pause, you can do that so that you can calculate it. Again, as h is tending to a 0, so 2x minus 3y minus 4 is the answer. So all we have done is that you see first we calculated in terms of y keeping x constant. Now I am doing x keeping y constant. Simple algebraic formula, cancelling out the positive and negative leads to this. Now you see this is the volume of a cone. Okay, this h is the height and r is the radius. So the volume of a cone depends on the cone's height and its radius r. Now as per the formula, if I go by the formula of the cone, this one is the volume formula, pi r squared by h by r, which represent the rate with which cone's volume changes if its radius is varied and its height is kept constant. So here the radius is changing and the height is kept constant. The partial derivative of v with respect to r is this, del v by del r equals to 2 pi r h by r. And this represents actually on the top hand side, this one is which represents the rate with which a cone's volume change if its radius is varied and its height is kept constant. So the partial derivative with respect to h is this one, pi r squared by r, taking a derivative of del v by del h, right, which represents the rate with which the volume changes and if its height is varied and its radius is kept constant. Now the total derivative of v with respect to r, this one. So you see that the total derivative with respect to h comes to this. We have differentiated v in terms of r, and this one on the top which comes 2 pi r h by 3 is actually del v by del r, and this part is del v by del h. And if we differentiate del v in terms of del h, so this comes at pi r squared. This one is actually this one, del v by del h and del v by del r. So actually it shows that the value of total derivative with respect to h and how we can differentiate the cone where we are keeping one h constant, r varying, and r constant, h varying. So this gives you a kind of an idea in terms of calculating the derivative of cone and the total derivative with respect to h. This is the next problem. So what if x comma y equals to x cubed plus y4? What is the partial derivative of f with respect to x? So this is very, very simple. You can do it mentally actually. We can use the power rule. So f prime of x equal to 3x squared plus 0. So we just put this as 3x squared. So what it has happened is that x cube has become 3x squared, and this is the final result. So it's quite simple. Now coming to the third problem, this is another expression. We have seen 2x raised to the power 5 plus 3y5. What is the partial derivative of f with respect to x? So what we will do is that we will use the power rule to differentiate 2x5 and x squared, because we, as I told, we are using x first, and we will treat 3y5 minus 8y squared and z squared as constant. So f prime of x would be this one. We are using the power rule. So 2x5 turns to 10x4, 0, and plus 2x this means, and this one becomes 8y squared z squared, which further leads to this. So this actually shows the problem. In this way you can use power rule and differentiate. So it becomes 10x4 minus 16x squared y squared z squared. You can use further to do this. Okay, so here is a torus. Again, this is a geometrical problem, and what we need to do is that what is the rate of change of volume with respect to r when r equals to 3, that is a small r, and the big R changes to 8. So volume of a torus we know is this, and we, by rearranging, we can write it as this, right? So 2 pi squared capital R r squared. And what we have done in this blue arrow, I have shown that I have differentiated this particular part, and it becomes 4 pi squared capital R, and this leads to this, and it leads to 4, 8, 12, 12, yeah, so it leads to, yeah, 32 multiplied by 3 equals to 96 pi squared. This is true when r equals to 3 and capital R is substituted as 8. So you see, this is a typical torus volume problem where there are two variables given, r and sub r, small r and big R, and how we use differential, partial differential to calculate this value. So we go further and we take this a similar kind of a torus, but here we are changing with terms of A, that is the area. We say that as a surface area, not specifically an area, because there's a difference between area and surface area. 4 pi squared, capital R, small r, it leads to this, and it leads to this, and this leads to 212 pi r squared when r equals small r equals to 3. I have not differentiated in terms of capital R, so this is a kind of a problem which gives you the torus area. This is another problem, calculating del z by del x and del z by del y in terms of x and y when z equals to x squared plus 3xy plus y minus 1. So what we will do, our strategy would be taking del z by del x, treat y as constant and differentiate with respect to x. So what we do, we have this, right, using the rules, and then we get, so this one equals to 2x plus 3y. And similarly, I have written deliberately y because we are treating y as constant. It equals to 3x plus y. Simple. So this leads to the seventh problem, which is this one. We have given three values, 2 by 3, 1 by 3, and 2 by 1 by. So we have z equals to this one, y minus x squared minus y squared whole raised to the power 1/2. But we want dz, right, by del z by del y. We want this. But the values of x and y are this. So, but we know del z by del y equals to this, which leads to this. So we are substituting the values of x and y, which is 2 by 3 and y by 3. We get this, and it gives to this. So again, you can make a pause of this video and you can take a note if you really want to check things out. So this is another kind of a problem using partial differentials. So final result is minus half. So if we are dealing with function of 3 or more variables, where is a general notation y equals to function of x, y and z and so on, we are taking 3 variables. For example, w equals to x sine of y plus 3z. So here what we have done, this means differentiating with respect to x, holding both y and z constant and so on. So you understand, I think, that what it actually means. Let me go back to the previous one. So when we are dealing with 2, it comes to this. When we are dealing with 3, we have to hold the first one constant, and then we have to differentiate keeping both the other two constant. We take one variable, that is x, we differentiate it, and we hold the y and z constant. We will be dealing with more variables in other videos where it deals with 3 or more variables. Now say for example, we get, let z equals to a function of x, y be a function. Then what we can do, I'm just writing so that it becomes clear. This one means the second derivative with respect to x holding y constant. So del squared z whole upon del x squared, it is the second derivative. It is just the similar as the ordinary derivative, but just we are using a curly d, so this is 1. This means the second derivative with respect to y keeping x constant. Earlier was with respect to x keeping y constant. This is y holding x constant. This one means differentiate first with respect to y and then with respect to x. Note that this is actually this one which you found, del squared z upon del x by del y. This is what we call the mixed partial derivative. It is outside the scope of this video, so we won't be dealing with this. So just keep it a note that it's called a mixed partial derivative, and it's the general result del squared z by del x by del y equals to del squared z by del y by dx. So it has got the same importance. So this is actually something what it actually means in terms of second derivative. So we come to the another problem. If we get this kind of an equation, 4x squared minus 8x y raised to the power 4 plus 7y5 minus 3. So how do we find that? We need to find out all the first and second order partial derivatives of z. So what we do is that we do this and we do this, and then we get the values as 8. Then we go forward, del squared z, we get into this, and we get this, and we get this. So all you can do is that what I'm doing is that I'm doing the same ordinary differential equations rule. We are using the power rule, sum rule, etc., and going one by one forward and calculating the values. Again, you can take a note and solve things out. This is further continued here. We get this one, we get this, and we get 32, and then del squared z del x by del y gives to this and gives to this. So I think that this is something which is quite clear. So this is how we generally solve out equations, and you can do using this rule. Now subscript notations for second order partial derivative, if we take a kind of a z equal to f of x, then what we can write is z, as I told you, subscript can be written as this, can be written as this, or can be written as this. So you see del x dy, del x dy, del x del y, and del y del x, it is the same as long as you're keeping the numerator del square z same. So this is the subscript notation for the second order derivative, partial derivative, which is outside the scope of this video. However, it is just good to keep a note on this and note that how the subscripts are written in these forms. So we come to another problem. We need to find out the partial differential coefficient for this expression, right? So what we do, this is quite simple. We write this one, and then we differentiate del y by del x, and we use the power rule. So we write 4ax plus 3by. I put these arrows just to note that this one is differentiated as 4ax and this one is differentiated by by. You note that we have kept b and y because we are differentiating first with respect to x. Then we use this one same, and we use this. So again, you can take a note. I have just shown, by various simple examples how things are proceeding. 3bxy again can be written as this. So what we are doing is we are using the same rule in order to differentiate it. So another problem, this is a pretty straightforward. If we get this kind of a equation, then we write this one. And you see what I will do is that the problem says that find the partial differential coefficient with respect to x, y, and z. First, we will do this one. So you see x squared yz becomes 2xyz by the power rule. Xy squared z becomes y squared z. Xyz squared becomes z squared y. And x squared y squared z squared becomes 2xy squared z squared. And I have just shown in this way, like one by one. It goes forward with this and it goes forward with this. Again, if you want to take a note, you can do that. These are simple examples which will solidify the foundation of solving partial differential equations, and I've just shown step by step how you do one keeping other constants. So I think by this time you don't have this conviction in your mind that partial differential equations are, so this is a relatively simple partial differential equation, and this is also what I have shown in this screen. So del u by del x is independent, and this is the general solution, which is similar to the ordinary differential equation. Okay, so partial differential equation can be also written if I take a function and expand it to up to n terms of variable. This is just a kind of a note. You can note that it can be also written in this form. So we come to another problem with this function of x, y, two variables, 3x squared y. How do we solve? So we will go step by step. So first we will treat y as constant. We can find partial of x, which is this one, which leads to this one, which is this one, and the final answer comes to 6yx. So again, you can take a note how we have solved this. Again, treating x as constant, we can find partial of y, which is this one, which leads to this one, which leads to this, and this is the answer. So this is how step by step we can go ahead, first treating y as constant, finding the partial of x, then treating x as constant, finding partial of y. So whatever partials that we are finding, it goes on like this. So you see, we find partial of x, x is at the denominator. We find partial of y, y is at the denominator. So this is, you can take it as a general notion. We are coming, I think, to the last problem. This is calculating del f by del x and del f by del y for the function by holding the opposite variable constant, this one. So what we can do is that we can calculate del f by del x and treat the variable y as constant and then differentiate in terms of f sub xy. Let us see how we proceed. So if we first take this one, and we get this long of equation. So again, you can take a note and you can see how del by del x equal to x squared, then 3xy, but this and this and this and this. I have noted this one because here the derivative of the third, fifth and sixth term, which we will see, are all 0. Why? Because they don't contain the variable x. so they are treated as constant. The derivative of the second term is also equal to the coefficient of x, which is minus 3y. Let us proceed, things will become clear. So yes, this is the one. Oh, so you see there, let me go back to the previous one so that things becomes clear. So this was the entire equation, this, so 2y squared, 5y and 12, they are becoming constant. So yeah, so these third, fifth and sixth terms are all 0, which leads to this. So 2x minus 3y minus 4. Then we do differentiate in terms of y, and how we do, we get this and this and this, which leads to minus 3x plus 4y plus 5. Here also I have not written in red, but as you can understand, those values which are constant are considered to be 0. So that is the end of the video. I hope you liked it, and please put up your comments, because I got a very good comments this time with many eager listeners and learners of physics and mathematics. Actually, it keeps things high on the moral, and you understand that I take a lot of effort in making those videos, then putting up them with visuals. So I think you will like it. Please do subscribe and click on the bell icon so that you can keep on getting updates from Physics for Students. So I have planned a couple of few videos which are related to partial differential equation, which I will be doing one by one. The first one would be this. Okay, these Greek symbols always create sometimes a confusion among young learners. So I will make a video where I can show the difference between these Greek letters. What do they mean? I will try to make a video on what is meant by curvature of a curve, how to measure a curve, and finally high order partial derivatives and how we can calculate this. So this is my agenda. Immediately for the partial differential equation series, I will be making 4 videos on these particular topics. I know that I am missing out on the metric tensor part, but because I'm dedicating a little bit more time in calculating and knowing in partial differential equations, this is the crux of mathematics. So hope you can bear with me. I will be coming up with the remainder part of metric tensor in my Einstein field equation series, and this is my plan of taking partial differential equation forward. I hope you liked it. Please put up your comments, like, share my channel as it keep on growing, and I'm also working on topology, which you have seen in introductory video. So I hope you're staying safe, and please keep yourselves safe and happy and your morale is high during this time. Bye, and do take care and have a nice day.